All right, beautiful class. This is, where are we? The last section of chapter 18? Let me see. Yep, cool. All right, so remember we were talking about delta G, the free energy. I want to just kind of remind you of a few things. We said when delta G is less than 0, in other words, if it's negative, that the reaction is spontaneous. In other words, it occurs at regular standard conditions. It just happens without any, I need to retract what I just said. It just occurs under certain conditions without any outside influence. But if delta G is greater than 0, we call it non-spontaneous. We also said that if you have a reaction like a, should I have a piece of paper back here? Nope, I need one. We also said if we have a thing like A plus B, a reaction, in equilibrium with C plus D, and that this reaction is at equilibrium, we said that the reaction going this way and the reaction going this way, if they both have to be going, which they would be at equilibrium, that the delta G would have to equal 0. And that's because, again, delta G in the forward direction would have to be less than 1, but delta G in the reverse direction would also have to be less than 1, or less than 0. And the only time that can happen, the only time you can have negative delta G's in both directions, it doesn't happen. So the best compromise is that delta G equals 0. So at equilibrium, delta G is 0. That's just kind of a brief refresher of free energy. All right, so now let's get into this. So there are two equations we're going to learn today. The first one is this one. And it's that under standard conditions, which is what that little dot here means. This just means that it was tested in a lab under standard conditions. Depending on the book, you will find different ideas for what quote-unquote standard conditions are, but generally we're talking about 298 K. This is different from standard conditions of gases where it's at 273 K. So it's kind of an annoying facet, but unfortunately it's just there. So we're talking about standard conditions in a lab, 298 K. It doesn't necessarily mean that it was at equilibrium at this point. It just means that that's where it was at that time. All right, so it says consider the reaction at 298 K. It gives you this, and it asks you to calculate delta G. All right, so one of the first things I noticed, even though it has nothing to do with it, is that we had 3 moles of gas and then we went to 2 moles of gas. Right, so we know that that it was the delta S, the entropy, ended up going down, but that has nothing to do with anything. So let's do this. Our delta G of a reaction is equal to delta G naught of the reaction plus RT ln of Q. We know we're using Q because it gave us various concentrations instead of just giving us a K. And it didn't tell us that it was at equilibrium or anything like that. It just gave us this. So let me grab my calculator here. It would appear I gave all my calculators away, but I've got this one. Unfortunately, I don't like using this one because it's a graphing, and you guys know how we feel about graphing calculators. So sorry. Okay, so we have our delta G of the reaction, which is asking for, is equal to this one in the standard conditions, which it gave us, negative 71200 joules. We're going to put this into joules every single time. And that's because you'll find out that the R over here uses joules. The R over there is 8.314 joules over mole Kelvin. So this is that. This is that. Our temperature said it would happen at 298 K. And last but not least, it asked for Q. Q is from the last chapter, but let's talk about what Q would be. Remember, Q is products over reactants. So our products was this NO2, and it tells us that NO2 was 2 ATM. So we'll have 2 ATM squared divided by our reactants, this NO, which is 0.1, squared, times this O2, which is also 0.100. These squares, again, are coming from the coefficients here and here. All right, so if we throw this into our calculator, 2 squared is 4, divided by, don't forget to use parentheses if you're going to use them, parentheses, and then the quantity 0.1 squared times 0.1, and parentheses. And I get an answer of 4,000. So I'm ln of 4,000. If I take the ln of 4,000, I get an answer of like 8.2 something, I believe. But I'm just going to do this all in one fell swoop. So I got the ln of 4,000 times 298 times 8.314. And I get an answer of 991,000. That seems pretty crazy. So let's do it again. The ln of 4,000 times 298 times 8.314 gives me an answer of 20,000. Makes a lot more sense. I wonder if I did the ln. Plus 20,549. Okay, and now we just add those things up. And I get an answer of 5651. So specifically negative 5651. And again, this is in joules, which would also equal negative 50.6 kilojoules, which again, we should be comfortable switching back and forth. Now, the problem of sig figs has come up several times lately. So what I want you to do is just ensure you use all the numbers from this if you have to apply that to a future calculation. So use all these numbers, don't use this one because you'll sometimes maybe end up with the wrong answer. So you want to stick with at least the number of sig figs you need plus 2 more. So that's why I want to stick with 3 plus 2 more would be 5. And that will usually get you a pretty strong answer. And it will come up. All right, moving on. So at equilibrium, Q equals K. We talked about that a lot in the last chapter. Also at equilibrium, we said the delta G of a reaction equals 0. So, and delta G of a reaction equals 0. So if you remember, our last problem was delta G, or our last equation, delta G naught plus RT ln of Q, right? This was our original problem. Now, at equilibrium, this goes to 0, and we could put Rx in because we're talking about a reaction here on all of them. But again, that's kind of a formality at the end of the day. So this is going to be 0. In other words, right now we have 0 equals delta G of the reaction plus RT and T ln of Q. But again, we're at equilibrium, so Q actually equals K. And now if you subtract that from this side, you have negative RT ln of K equals delta G of the reaction, right? Or sometimes we flip it around. In fact, usually we flip around, we say delta G of the reaction equals negative RT ln of K. In other words, negative root link is kind of how I remember it, and that's what we got right there. All right, so, and sorry, I should put little duty buffers on there. Okay, so again, at equilibrium, this would be 0 because it's at equilibrium, and that Q would be K, and that's how we end up here. All right, so there's a few things to think about. When K is less than 1, our negative, our delta H of the reaction, or delta G of the reaction is going to be positive. Let's talk about why that is real quick, because it is kind of an important concept. If we have A plus B, and then C plus D, and to keep things consistent, I'm only going to focus on reactants going to products. Reactants going to products. There's a lot of different stuff written here, and that's all true, but I think it helps if you only focus in one direction. Okay, So remember that if K is less than 1, like let's say we have a K that's like equal to 0.25 or something like that. So that's less than 1. That tells us, remember, K is equal to products over reactants. That K being less than 1 tells us that this number is bigger, that there's more reactants than there are products, meaning there's more stuff over here. There's more stuff over here on the reactant side than there is over here. These are the reactants, by the way. These are the products in our beautiful situation here. All right, so it's telling you there's more reactants. So in a spontaneous reaction, remember, we're looking to see if stuff goes this way, if it wants to go from reactant to product. But if K is less than 1, we automatically know that it doesn't want to go that way. It wants to go this way, right? So it's non-spontaneous going this way, or non-spontaneous going in this direction. In other words, you can, just from the K, you can guess that if K is less than 1, then delta G is going to have to be positive, meaning non-spontaneous, if that makes sense. All right, the opposite is true if we have a K that's greater than 1. So like, let's say, if you had a K that's like 4,500 or something like that, remember it's products over reactants. So it's telling you there's a ton of products, meaning it wants to create products. It wants to react that way. So if it wants to react that way, then your delta G is going to be negative. And that's what you get. So if K is greater than 1, your delta G is going to be negative. And then when K equals 1, we already knew that that's a condition for it being in equilibrium. We also know that the delta G of the reaction is going to be 0. All right. Let's see. And it says the reaction happens to be at equilibrium under standard conditions. So it just happens to work if this were in standard conditions and it was in equilibrium. Okay. Use tabulated free energy of formation to calculate the equilibrium constant at this. Okay. So we have a general idea now. Because knowing when K is less than 1 or greater than 1 is actually very helpful in an exam. In terms of guessing what the answer may or may not be. And I love when you guys think things through, even if you don't know the answer. If you just put what you think it should be and why, that's usually pretty helpful. Okay, so it says, use this tabulated free energy for this. All right, we might not know what's going on right away, and I don't have any other information on that problem, I don't think. Yep. So it seems like a very limited amount of information, but it's not fully, because we know one thing. We know that we can calculate the delta G of the reaction. And we know that's going to equal our products, the sum of the products minus the sum of all the reactants. In other words, our products was this NO2, and we have 2 moles of it. So we're going to say 2 mole times whatever the NO2 was, 51.3, minus 1 mole times the NO2, which is 99.8. And those are kilojoules per mole. I should have written in the other one because mole cancels, and this would have been kilojoules per mole as well. All right, so we have 2 times 51, so 102.6 kilojoules minus 99.8 kilojoules, which would give us 2.8 kilojoules, okay? And to remind you, we just calculated the delta G of the reaction. But that's not what it asked us to do. It asked us to calculate the equilibrium constant, so we're looking for K. That's okay, because we have the delta G, and we know how delta G relates to K. We know that this delta G equals negative root link. In other words, negative 8.314 times 298K. How do we know it was 2 out of 98? It's because it told us. And that little dot. All right, times the ln of K. And that whole thing is equal to 2,800 joules. Okay, so we have 2,800 joules, and I'm going to divide each side by 8.314, by that negative 8.314 times 298K. Negative 8.314. And when you do this, 2800 divided by 8.314 298, because I didn't use parentheses, so you just use division twice, and I didn't add a negative, but I get an answer of delta G equals negative 1.13. All right, cool. So, or excuse me, yeah, negative 1.13 equals the ln of K. I can do it. What am I doing? All right, so all of this stuff equals the ln of K. All right, but we're not done yet because we gotta solve for K. In order to get rid of this natural log, we're just gonna take Miller's number to each side, this E to each side. And what that does is it essentially cancels that out. And so we have E negative 1.13 equals K. So I'm gonna take E, which happens to be this button right here, and then to the negative 1.13. And I get an answer of 0.32 as my final answer. My question to you would be, does that make sense? So when we were back up here, we had a positive delta G, right? So positive delta G tells us that this is not spontaneous. Again, because it's positive. And even better than that is we can predict what our K is going to be, because remember, if it's not spontaneous, it doesn't want to go from reactants to products. It prefers reactants more. And therefore, we expected our K to be less than 1. And that's what we ended up getting. So that's a good check. Our K is less than 1. All right. Here we discuss the temperature dependence on the equilibrium constant, which we kind of already have done a little bit. We certainly have explored this one right here. But I just want you to see the connection between y equals mx plus b. So if I say this on the topic list for your exam, then I'm going to include some sort of equation of the line, or wanting to know how to graph something, you know where to look. So if I wanted you to, for example, find the delta H of a reaction, and I give you this information, or ask you to draw a graph or something, you know that the y is going to be the ln of K, you know that the x is going to be 1 over temperature, and you know that the slope, big or positive or negative, whatever it's going to be, is going to be delta H of the reaction over R. Cool? So mainly this is all I would ask you, like what are the units of the slope, or maybe what would be on the y-axis, etc. So those are the things to look for. This we didn't use in the last class, and you even had an exam question about it, so I'm just gonna keep it going. All right, number 19 is oxidation reduction refresher. Okay, let me grab some water for this one. All right, so we have we've had the disservice of not spending too much time going over naming, etc., because that was done in Gen Chem 1. And knowing naming is actually really helpful for redox, etc. But before we get there, I'll kind of hopefully work through it with you. But if you need help on naming, this is a good place to stop and go refresh yourself, especially with ionic compound naming. Okay, so reduction, oxidation reactions. We're going to start by talking about oxidation number. Which we denote with an ON. Okay, there are a few rules to determining oxidation number. The first one is that things alone are paired with selves. Things alone or paired with themselves are always going to have an oxidation number of 0. So for an example, H2, that's alone or paired with itself. Copper, aluminum, S8, N2. All of these would have an oxidation number of 0. Number 2, H in a compound. So whenever H is paired with something other than itself, it's going to be +1. Notice when we've written charges in the past, we always put the charge after the number, but when oxidation numbers, that's when you put the charge before the number. Nobody really cares though. I don't. So when you have oxygen in a compound, the oxidation number is going to be -2. So an example would be like water, H2O. All right, even though there's 2 hydrogens here, we only write the oxidation number of a single one of them. So here we'd put 1+. So if I asked you for the oxidation number of hydrogen, you're not talking about this hydrogen or that hydrogen. You're telling me the overall oxidation number of the hydrogens in there is just 1. And then -2. So only report for 1. All right, number 4 is ion. I'm going to do ionic stuff. Okay, these are the things that make up ionic compounds. So, for example, if you have carbonates, its overall oxidation number is going to be its charge. Same as charge. Its overall oxidation number is going to be -2 because the charge was too negative. If you have something like copper 2+, the overall oxidation number is going to be +2. And if you have something like copper carbonate, copper 2 carbonate specifically, the oxidation number of copper would be -2. The oxidation number of this carbonate would also be -2. That's kind of like how you would write it. Okay, then we have something like, let's say, zinc oxide. So in zinc oxide, we know the oxidation number of oxygen is -2 because it's in a compound. But because of that, we also know zinc must be 2+ charge. Oops, sorry, that's minus. Zinc must also be 2+, that's why it's got a +2. In aluminum chloride, the aluminum must be +3 because this is made up of aluminum 3+ and 3 chlorides. So aluminum must be +3. And even though there's 3 chlorides, remember we only report just one of the charges as -1. Each one is -3, but we only report the -1. And it will make more sense here in a minute. All right, so number 5, all oxidation numbers must add up to overall charge in the compound. So all the oxidation numbers must add up to the overall charge in the compound. All right, so let me give you an example. Let's say we have copper nitrate. So we would generally say this is made up of copper 1 and nitrate. So we want to say that this is 1+, or +1, and this is -1, and you're right. But what if we broke down this nitrate even further? Let's say we want to know the oxidation number of everything in there. Well, the oxidation number of each oxygen is -2. We know that. But how many are there? There's a total of 3. So in total, all of our charge from that oxygen is actually -6. And we know that we're going to add that to something to get an overall charge of -1 because that was the charge of this nitrate. So something plus -6 must equal -1. That something has to be a positive 5. 5 minus 6 equals -1, and that's the only reason that this is a 5. But again, we only report that for a single one of those oxygens, even though all 3 of them added up to that -6. Let's do another example. SO4, 2 minus. Let's look at sulfate and say I want to break it down. So our overall charge of the sulfate is -2. And we know that the sulfur plus 4 oxygens has to equal that -2. We know that each oxygen is -2 because it's oxygen. But again, we have 4 of them for a total of -8. So we know that some amount of sulfur plus -8 must equal -2. What must sulfur be? Sulfur has to be +6. +6 plus -8 equals -2. The only thing sulfur can be is +6. All right, so understanding how to assign oxidation numbers becomes pretty important. So let's do some example problems for how that works. All right, so let's say I have a reaction that is this. Zinc plus 2HCl reacts to form ZnCl2 plus H2 gas. Okay, and I want you to assign oxidation numbers to each of these species. So our zinc and our hydrogen, they're alone. And that's when I usually get excited. I'm like, woo, sweet. Because it's easy to forget those and get bogged down, and maybe you'll accidentally assign this one a +1. So if you can get in the habit, right away give all your zeros, put all your zeros out there. And now we can look at these two. So this hydrogen is in a compound, right? That makes it +1. This chlorine is in a compound. That makes it, well, is in this specific compound, so this is actually H plus, Cl minus, right? So it has to be -1. All right, now we look at zinc and chloride over here. We know that there are 2 chlorides and each of them has to be -1. So we write just that for just the one for the one of the chlorides, again, not for both of them. And it's a hard habit to get used to. But this is a zinc 2 plus and 2 Cl minuses. So again, each chloride is -1, that zinc is a +2. All right, we have assigned oxidation numbers. Good job. The reason we're doing all of this is so we can find out what's oxidized and what's reduced. What's oxidized and what's reduced. Okay, so I like looking at the reduced first. In other words, the reduced thing is going to be the species whose oxidation number went down. It was reduced. So, for example, hydrogen here started at a +1 and it went to a 0. If you had $1 and now you have $0, I think you'd agree your money was reduced. It went down. And that's why H is a thing that was reduced. Sometimes they'll ask for the full species, sometimes they'll talk about agents, but generally if you put just the element H, you are fine. Okay, and then we're going to look at things that were oxidized. Chlorine, notice, was a -1 and a -1, it didn't change. And this is the reason that it's kind of so important to put just one of these on there. Because if I'd put a -2, it would have looked like chloride was reduced, but it wasn't, right? So we're only reporting the oxidation number of just one of the species. All right, and then zinc goes from 0 to +2. It went up, that's because zinc was oxidized. So the one that goes down is reduced, the one that goes up is oxidized. All right, let's do another example problem. Actually, let's not. I think I have this. And the next problem, we say which are oxidized and which are reduced in this problem. All right, so first things first, look for your zeros. Easy to forget them. Woohoo! Yeehaw! Sweet, good job. And now we're gonna go through and look at the oxidation numbers of everything. Remember the rules. If hydrogen's paired with something, it's got a 1 plus, or a plus 1, excuse me. Yeah, plus 1. And if oxygen is paired with something, it's got a -2. It's that simple. So if this hydrogen is paired with something, boom, plus 1. Is that oxygen paired with something? Boom, -2. Is this oxygen paired with something? -2. Is this hydrogen paired with something? Plus 1. Now pretty much the only thing we have to figure out is calcium. You know this is calcium hydroxide, meaning it's calcium and 2 OH minuses. That calcium must be a 2 positive charge then. And we have all the information we need. Now you'll notice that this hydrogen and this hydrogen are the same, but don't miss out on the fact that this one over here got lower. In other words, it was reduced. And that's why the answer to this, of what was oxidized and what was reduced, the reduced thing was hydrogen. The oxidized thing goes from 0 to 2 plus. That was the calcium. All right, moving on. Balance and half reactions. Okay, so hopefully this made some sense. This is going to become imperative when you'll eventually realize that the thing that's oxidized is going to be the anode, and the thing that's reduced is going to be the cathode. I didn't go over this in class. I probably should have, but we'll get to it. Notice that the vowels stick together. Ayo! The vowels stick together, and here the consonants stick together. And that's kind of how I remember them. All right, so this will come up in later chapters though. All right, let's learn to balance half reactions. I'm gonna go get some more paper. Okay, so to balance half reactions, or any redox reaction, it's going to take a few different steps, right? So we're going to start with this one. I think it's pretty straightforward, thankfully. The first things first, let's talk about why we're balancing it. So remember, when we add up charges on both sides of the reaction, they should be equivalent. So over here, when I add up all these charges, I get a total 2 plus charge. And when I add up all these charges, I get a total 3 plus charge. Hopefully you agree 2 plus does not equal 3 plus, and therefore this thing is actually not balanced as written. Even though, yeah, 1 aluminum, 1 copper, 1 copper, it's not balanced. Okay, so to balance it, what we're gonna do is split them in the reactions. You can kind of look pretty quickly and see copper here was reduced, aluminum here was oxidized, and those right there are your half reactions. We're gonna look at the aluminum going to Al3 plus, and we will also look at the copper, 2 plus, being reduced to solid copper, okay? I generally don't write aqueous just because it can kind of get messy, especially with a pen like this. But also, if something's an ion, it's going to be aqueous, unless you're talking about some kind of crazy gas situation, which I don't think we addressed in this class. Okay, so first things first, we're gonna add electrons to balance it out. So add electrons to balance. Every electron is a negative charge. So let's look at this first one. Over here we've got 0, and over here we got 3 plus. So we have to add 3 electrons to this side for the overall thing to be balanced. Now we have a 3 plus and 3 negatives, which total the 0 that's over here. 0 plus 3 minus 3 overall gives us 0. And this thing now, this half reaction, is balanced. Let's look at this one. Here we've got 2 plus, copper 2 plus, and copper. So we know we need to add 2 electrons to this side to get it to balance, because negative, 2 negatives plus a 2 positive is going to equal 0, and that's what this equals over here. So now both sides of the reaction equal 0. Yay! All right, now generally you want to add these two things up. But you can only add them up if the electrons on the left are the same number as the electrons on the right. You can see here that here I have 2 and here I have 3, and we're going to have to use the lowest common factor to figure out what to do. So right here, and that would be 6. So right here I'm going to multiply this whole thing by 3, and right here I'm going to multiply that whole thing by 2. And that will give us 6 electrons on the right and 6 electrons on the left for when we add them up. All right, let's go ahead and write it out though. So right now, if I multiply this whole top equation by 2, I get 2 aluminum, yielding 2 aluminum 3 plus 6 electrons, which is what we're going for. And this copper side, I get 6 electrons plus 3 Cu2 plus, all yielding 3 coppers. All right, and now we're good to go ahead and add them up because we have the same number of electrons on both sides, this plus this. So we're just going to add these up. We get 2 aluminum plus 3 of these copper ions, yielding 2 Al3 plus 3 CuS. Okay, so that would be our overall balanced reaction. Now one fun check, or one really good check that you should get in the habit of doing, is ensuring the charges on the left equal the charges on the right, and that will generally tell you if you did things correctly. So here I have a 0 plus 3, 2 pluses, for a total of a 6 plus charge over here. And then I look over here, I've got 2 3 pluses plus 0 for a total of a 6 plus charge over here. This thing's balanced, and this is a good answer. Sweet. Moving right along. Let's go ahead and take that fun concept and make it more miserable. Just kidding, we're making it more fun. It's awesome. This is kind of a continuation of what we just did. Just with a few more nuances. So the directions have been kind of split here. So you split into the half reactions, you balance manganese with water, you balance water with H+, you balance electrons, blah, blah, blah. These are a whole bunch of words until we do it. So let's just do it. Okay, so the reactions that maybe you can see is that we have iron here going to Fe+. This looks like it was oxidized. And this one right here, going from here to here, was reduced, but I'll show you why. Each oxygen is -2, so we have a total of -8. We know that they must add up to equal -1, so manganese, excuse me, so manganese must be +7. So it went from a +7 to a +2, so it was reduced. Now you take those whole compounds of everything that was oxidized and everything that was reduced, and you break them into their half reactions. Okay, so let's do the iron here. So we're going to take this one, Fe3+, and when we want to balance it with electrons. So over here, I've got a 2+, over here I got a 3+, so I know I need to add more negative to this side, specifically 1 negative. So now over here I have a 3+, plus a 1- for a total of 2+, which is also what I have over here, so that checks out. And now we can move on to this next part. You're gonna move the whole species down here, this whole permanganate, yielding Mn2+. All right, and our instinct is to immediately balance with electrons, but you'll find out that doesn't work very well. So what we're gonna have to do right away is follow the steps. We have to pay attention to what kind of balance we're doing. We're balancing in acidic conditions. So pretty much anytime you see oxygen that's not balanced on both sides, you pretty much know you're going to be asked to do acidic or basic conditions. So make sure you look and see which one you're doing, because they differ. The good thing is they are pretty much all the way the same. The acid has all the steps that the base has, but the base just has a couple more steps. Okay, so step number 1 is we split it into half reactions. Step number 2 is balance the oxygens with water. All right, what I mean by that is over here you have 4 oxygens, and over here you're gonna add 4 waters. The reason you're adding 4 waters is because each water has 1 oxygen, and again, we need it to balance the oxygens with water. All right, great. Number 2 though, now hopefully you realize you introduced some hydrogen in there. You specifically 8 hydrogen. So now over here, we're gonna balance that with 8 H pluses. That's the acid portion of what we consider the acidic stuff. Okay, so we balanced it with water with the H plus, and now we can look at the total number of electrons. So if we count total number of electrons over here, we have a positive 8 plus a negative 1 for a total currently of positive 7 over here. And over here, we have positive 2 plus 0 for a total of positive 2. So where do we need to add electrons to and why? We're gonna add it to the most positive side to reduce that to equal this. So how many electrons do we need for 7 to go to 5? Or for 7 to go to 2, we need 5 electrons. So I'm gonna add plus 5 electrons over here. Okay, that now is a balanced reaction. We have the same number of manganese, same number of oxygens, same number of hydrogens, and we also have the same charges, and that's why we know that we're okay. All right, now we can go back through and add them back together. But before we do that, we have to make sure that they have the same number of electrons. This has 5 here, but this, if you remember, only has 1. They have to have the same number of electrons before you can add them together. So we'll have to multiply that by 5. So if I were to rewrite that reaction, it would be 5 Fe2 plus, yielding 5 Fe3 plus 5 electrons. All right, now we can add these suckers up. So we had 8 H pluses plus MnO4 negative. Our 5 electrons cancel. Remember when you have something on one side of the arrow? Oh, I'm ready. You can't even see it. 8 H pluses plus our MnO4 is where I was at. We have 5 electrons here and 5 electrons here, so they cancel. If they don't cancel, something went wrong. Plus 5 Fe2 plus. And now we can get to the product side. Over here we have Mn2 plus 4 waters plus 5 Fe3 pluses. Cool. Okay, so we are almost done, but it always helps to again check and ensure charges on both sides equal the same. Here I have 8 plus 1 minus plus 10 plus. And then over here we have 5 times Fe3 plus for a total of 15 plus this 2 plus over here, also for a total of 17 plus, and that thing is balanced. So this would be your final reaction. All right, again, keep in mind that was acidic conditions. So just to remind you, first we balanced the oxygen with this, then we balanced it with the H pluses, then we added the electrons, made sure the number of electrons in each half reaction was equivalent, and then we could add it up. All right, let's do another one. Now we're going to talk about balancing in basic conditions. So step number 1 through 3 really are the same. I think that's kind of helpful. So let's do it. All right, now we're going to balance in basic conditions. All right, so if we were to look at these species, we'd say this one right here went from negative to positive. This was oxidized. and the manganese. So we went from a negative to a 0, and so that was oxidized. The manganese over here, we had a -1 plus -8 plus, so we had a total of -1. The total oxygen from here was -8 plus the manganese itself, so this had to be +7. And over here, it was just +4, so it was reduced. Kind of pointless to do right now. It's going to become pretty important later, but at least it makes us think about the half reactions, that we're sure that we're splitting them apart correctly. So here I have I-, and it's forming I2. This is a situation we haven't really encountered yet, and that is that we still need the same number of elements on each side. So when we're doing oxygen, it's very specific to whether it's acidic or basic conditions, but anything else, you can just straight up go and balance it. So here, for example, I have one I, and over here I have 2. So we're gonna put 2I-. All right, now we can balance with electrons. Over here I have a total of 2 negative, so I need to add 2 electrons over here. Now I can move on to this manganese. So we have permanganate, which you saw in class. It's easy to forget that negative. I kept forgetting it. Going to this MnO2. Notice there's no charge here because there's nothing written. All right, and again, your instinct might be to balance this immediately with electron, but keep in mind the oxygen on each side are different. So that's when you're like, wait, what are we doing? Yeah, we're balancing in a basic solution. So what that means is we're gonna have to follow a new set of rules that we haven't gone over until now. All right, so split into half reactions, check. Balance oxygen with water. All right, so just like in our last one, this has 2, and this has 4, so we need to add 2 waters over here. So now we have a total of 4 oxygens on this side and 4 oxygens on that side. Now we can balance with H+. Because we've added a total of 4 hydrogens, over here we also want to add 4 H+. So check, check, check. Add equal mole of OH- to each side of the equation to balance out the H+. What I mean by that is you don't want to screw anything up. Right now you've got the balanced number of oxygen and hydrogen, but we're going to add equal number of OH- to each side. 4 OH- plus 4 OH-, because it cancels out anyways. So what's the point of it? Well, you'll see. So let me write this better and bigger so you can see it. So right now I added 4 OH-. Why 4? Because I had 4 H+. You want to balance out the H+ with OH-. All right, now we can kind of see what happens to this, because if you have an OH and an OH- and an H+, that equals a water. So right now we actually have 4 waters. Again, because H+ plus OH- equals a water. So this gave us 4 waters plus permanganate, yielding MnO2 plus 2 waters plus 4 hydroxide. All right, so now we're at step 5. Now we can balance with the electrons. And then we can balance the half, so that each half reaction ensure they have the same number of electrons. So first, let's balance electrons. Over here, I see a total of -1 from this. And over here, I see a total of -4 because there's 4 hydroxides. So I have to add 3 electrons to this side. So now we have a total of -4 on both sides. All right, now we're almost ready to add them up, but remember, you have to have the same number of electrons in each half reaction so they cancel each other out. We're not at that spot. We need to multiply this whole thing by 3 and this whole thing by 2, so we have 6 electrons to the right and 6 electrons to the left that will cancel each other out. All right, let's rewrite these reactions just to make sure you're following. So I'm going to start with the I. I'm going to multiply everything by 3, so I have 6 I-, yielding 3 I2 plus 6 E-. All right, and I'm going to do the same thing with this one right here, multiplying everything by 2. 8 H2O plus 2 MnO4 minus plus 6 electrons, getting 2 MnO2 plus 4 H2O plus 8 OH minuses. Now, some of you might have already wanted to cancel out these waters, and you totally could have done it way back here. By cancel out, I mean you had 2 and you had 4, so you could have canceled out and just had 2 left over here. Could have done that. I didn't, because I didn't, and I'm being consistent with what I taught in class. Okay, now we're going to add them up. We have 6I minus plus 8 H2O plus 2 MnO4 negative. Our beautiful 6 electrons cancel, all yielding 3I2 plus 2 MnO2 plus 4 water and 8 OH minuses. Sweet. All right, so now we're looking okay, but we're not done yet. I see that there's 8 waters and 4 waters, so those can cancel. So what I'm going to do, I have 8 waters over here and 4 waters over here. So in other words, 4 of these guys will cancel. So cross that out. And now we only have 4 waters left over here. And last but not least, we want to check to make sure everything adds up. Here I have -6 from this, plus 0, plus 2 negative from this manganese, for a total of -8. And over here, let me make it better, 2 there, it was a horrible 2. Over here, we have 8 negative from the OHs, so -8. -8, -8, everything should be balanced, and that is our final answer. So, whew. See, aren't they fun? All right, that's as far as we got in class. So that is where I'm probably gonna stop. All right, y'all, have a great day, bye.